Hello everyone, this is Miss Patel Dane here for topic 8.1, Introduction to Acids and Bases, and topic 8.2, pH and pOH of strong acids and bases. So I would highly recommend going back through topic 4.8. That gave us an introduction to acid-base reactions, and we will need some of that information as we progress through this unit. Also, topic 4.6 will be helpful as we talk about titrations. So the first thing we're going to do is take a look at this chart. This chart compares temperature in degrees Celsius to kW values. So recall that kW represents the equilibrium constant for water. So if we look at 0 degrees Celsius, it's 1.14 times 10 to the negative 15th. 25 degrees Celsius is 1.0 times 10 to the negative 14th, and so on and so forth. So we're looking at this first question over here for A. Show the autoionization of water with an equation and particle diagram. So when we talk about autoionization, it means that we are taking apart water and breaking it up into its specific ions. So if we think about water itself, we have H2O. We can draw it as a bent structure, really known as the Mickey Mouse structure. And if we water itself needs to break down. So if this is, let's say, in a liquid, we can add heat and add some electricity in order to break it down. And this is going to be an equilibrium. So it breaks down into H plus and OH minus. And of course, any ions should be aqueous as well. This then breaks into one little hydrogen and then an OH ion. Oops, forgot my particle diagram that I was doing there. So make sure that's an oxygen with one hydrogen, and that should be a little negative. Ignore this little vertical line coming down. So our Kw expression would be Kw is equal to the concentration of H plus ions times the concentration of OH minus ions. And usually it's over the reactants, but recall that liquids and solids do not go into the equilibrium expression, so therefore this would just be the Kw is equal to the concentration of H plus times the concentration of OH minus. So as the temperature increases, we got to think about what happens to Kw. So Kw, as temperature increases, the Kw value itself will also increase and is endothermic. So there are 6 strong acids that you will need to memorize. We can get some little tricks in here to help us out, but for the most part, we deal with HCl, HI, HBr. So notice that this is chlorine, group 17. Bromine is right underneath it, and then there's iodine. So it's those 3 elements within group 17 combined with hydrogen. Notice that fluorine's not in here. Then we have something called sulfuric acid, or H2SO4, HNO3, or nitric acid, and then HClO4, which is called perchloric. So we'll write these down. So we have hydrochloric acid, hydroiodic acid, hydrobromic acid, sulfuric acid, nitric acid, and perchloric acid. And if we're going to take a look at what happens, any strong acids are going to completely disassociate. This means that they're going to completely break up into their ions, meaning it's not going to be an equilibrium. It's just a forward reaction. So let's say we have HCl. It'll break up into H pluses and Cl minuses. These are a 1-to-1 ratio. Same thing with H pluses and I minuses, or iodine ions. We have for hydrobromic acid, H plus, then Br minus, R minus. H2SO4 is a little different. It's a 2-to-1 ratio. For every 2 H pluses you have one sulfate ion, which is a -2 charge. So again, every H plus ion you have one sulfate ion, which is a -2 charge. Nitric acid is a 1-to-1 ratio. So for every one H plus, you have one NO3 minus. And HClO4, for every H plus that you have one ClO4 minus ion. And again, these are in aqueous because that's how you're showing the ions, so they're going to be completely disassociated. So next we'll go over to our strong bases. There are also 6 of these, but these actually might be even easier to remember. These are our group 1 and group 2 ions combined with OH ions or hydroxides. So we have LiOH, NaOH, KOH, RbOH. And then we can go through and do the group 2. So I'll just do a few of these. We have BeOH2. Remember, Be is a +2, OH is a -1. So it's a 1-to-2 ratio. And then MgOH2. There are more of these down the group, but these are just the ones I decided to give you here. I'm just going to show you the diagrams for potentially, like, let's do RbOH and BeOH2. This is a 1-to-1 ratio, so it's Rb plus 1, OH is -1. Whereas over here we have Be, which is +2, and there's 2 OH minus. To figure out the names, it's just the element's name and hydroxide. So for example, this one is lithium hydroxide. We have sodium hydroxide. Potassium hydroxide. And then we've got rubidium hydroxide, beryllium hydroxide, and magnesium hydroxide. So I'll have you guys fill those in. This is also my test to see if you are paying attention to what I'm listening to as opposed to what I'm just writing. So we can calculate what can happen between the pH and the pOH of ions compared to the concentration. So if we have something that's acidic, we can see from the previous page that we have a whole bunch of H plus ions. If we have something that's basic, we see a bunch of OH minus ions. So acids have H plus, bases have OH minus. So this is the H plus. This is something that is going to end up being the more of these that we have, the more acidic it is. For OH minus, the more of these that we have, the more basic it is. You've also seen the term pH. This represents the power of hydrogen. When they say hydrogen, meaning hydrogen ions. So if we recall, all of our elements have to be capitalized. So that's why it's a lowercase p and a capital H. If we think about this, go ahead and label this as your power of hydroxide ions. Or potential. Potential is actually even better to say for this. So potential of hydrogen ions versus potential of hydroxide ions. So we can convert between all of these things. And these conversions might seem intense as we go through them, but the more we do them, the better, or the more easily it'll be easier to understand, rather. So let's talk about H plus to pH. We know that and I'm going to switch this around. So the pH of something is equal to the negative log of the concentration of H plus. So we just put in our negative log of whatever that concentration is, and that gives us the pH. The same formula is essentially used for pOH. So the pOH of something is equal to the negative log of the OH minus concentration. If we flip it, meaning if we're trying to get from pH to H plus, we know that the concentration of H plus is equal to 10 to the negative pH. So if we think about log versus pH, to get out of log, use 10 to the negative whatever. Same thing over here. We have the concentration of OH minus is equal to 10 to the negative pOH. We then have to convert back and forth between potentially, let's say, like pH and pOH. We know that pH plus pOH is equal to 14. So that's really the one that you need to remember. And then the rest of these kind of make a little bit more sense. We'll put them in just because they're there, but we can say the pH is equal to 14 minus the POH. Let's say we're given pH when we get to POH. We can say that the POH is equal to 14 minus the pH. So again, it's going from where we're going from to where we're going to. And then up here, these work for at 25 degrees Celsius. So at 25 degrees Celsius, we can see that, and I'm going to flip back to this one, sorry, that the Kw is going to be 1.0 times 10 to the negative 14. So this Kw is 1.0 times 10 to the negative 14. That's equal to the concentration of H plus times the concentration of OH minus. So we'll rewrite that over here. Concentration of H plus times the concentration of OH minus is equal to 1.0 times 10 to the negative 14th. Just squeeze that in there. So the opposite, if I want to think about H plus, or I want to find H plus, but I'm given OH minus, I know that I have 1.00 or 1.0 times 10 to the negative 14th over the concentration of OH minus. Or if I'm given H plus and I want to go to OH minus, I can say that the concentration of OH minus is equal to 1.00 times 10 to the negative 14th over H plus. So really the things that we need to remember, I would say making sure that you know these are really important. That'll get you to the other two. And then if you remember maybe even how to do one of these, that'll get you over to here. And if you know how to get out of log, that'll give you this. But sometimes we don't remember that. So let's just make sure we have that. And the same thing happens between OH minus and POH. So let's take a look at some of these calculations. So what is the pH if the H plus concentration is 1.0 times 10 to the negative 5th molar? So let's grab, let's do the formulas in here first. So I'm trying to figure out pH. So I'm trying to solve for this, and I'm given H plus, which is right here. So I can use this equation. pH is equal to the negative log of the H plus concentration. So it's a negative log of 1.0 times 10 to the negative 5th. You might also remember from log that we're essentially getting rid of the 1 times 10. So essentially, this is going to be just 5. And we can throw this into our calculator just to double check, right? So we can say the negative log is, and I'm going to put, 1, don't forget the EE button, and on this calculator, it's right here, negative 5th, which should give us 5. This works if you have 1 times 10 to the something. If it's another number, which we're going to see in the next example, it's going to be close to that exponent, but it's not going to be that exact exponent. So doing B, pH is equal to the negative log. So sorry, we have to find pH. We're given H plus. So pH is equal to the negative log of 2.3 times 10 to the negative 5th. So this one we would have to put in our calculators because we don't have it's not a base number of 1.0. So this is 2.3. Going to use the EE button, negative 5. And that's 4.638, etc. Usually what we do is we take the base number here, and then that's how many digits after the decimal point that we use for sig figs. So pH has a different rule for sig figs. So again, we know we have 2 sig figs here, so I need 2 digits after the decimal point in this one. So my final answer ends up being 4.64. And pH does not have a unit, so it's a unitless number, and we'll leave it like that. Taking a look at C, what is the POH if the OH minus is 1.0 times 10 to the negative 5th? So we know that POH is equal to the negative log of the OH minus concentration. So negative log of 1.0 times 10 to the negative 5th. Same thing as we talked about before, that should be 5. Then we'll do the same exact thing that we did before to get us to our POH concentration, POH, if the OH minus concentration is 2.3 times 10 to the negative fifth. So I know that POH is equal to the negative log of 2.3 times 10 to the negative fifth. And for my calculations above, I had 4.64. One little note, sorry, with sig figs. I probably should have put 2 sig figs after this 5 to make that 5.00 because of that base number. Same thing over here. Sorry about that. And then E, what is the H plus concentration if the pH is 5.3? So I am here, I need to get to here. So I'm going to use this equation. I know that H plus is equal to 10 to the negative whatever the pH value is. So this is 10 to the negative 5.3, and then I will solve for that. So using this calculator, I will do second log, and that should be negative 5.3. So we've got a whole bunch of digits here. Move that decimal place over. We've got 1, 2, 3, 4, 5, 6. So it's equal to 5.0. Let's see, I have 2 digits there, so that's good. 5.0 times 10 to the negative 6. And then because this is concentration, that should be molarity. Over here for F, what is the OH minus if the POH is 3.4? So I know the POH, I need to get to the the concentration of OH minus, I'm going to use this equation. So the concentration of OH minus is equal to 10 to the negative POH. So 10 to the negative 3.4. So I'm going to do second, and then second log to give me to whatever the opposite of log is. So 10 to the whatever number. That's negative 3.4. And I know I need 2 sig figs. So I'm going to go 1, 2, 3, 4 spots after the decimal, to get into scientific notation. So this would be 3.9. However, to get that to 3.98, 2 sig figs would end up being 4.0 times 10 to the negative 4, I believe. And that is in molarity. So notice that this exponent's really close to this exponent, and this exponent's really close to this exponent. You know you're doing it correctly if that's what you end up getting. Right? And then our next set of problems. This time we have the POH, and we want to figure out the concentration of the hydronium ions. So that H plus is the hydronium ions. So we are here, we want to get to here. There's no clear path to do that. So you got to use one of the 2 paths to get there. It doesn't matter which path you use, as long as you do 2 different steps for this. So let's say for this one, I want to do, go from POH to OH minus, and then OH minus to H plus. So I can say that the concentration of OH minus is equal to 10 to the negative POH. The other equation I have is, actually we're just going to stick to this one first. So I have 10 to the negative 10.5, and that'll get me to my concentration of OH minus. So skip that, negative 10.5. So I have this time 3.16 times 10 to the negative 11. Ideally, we would not we would not round this too early, but in this case, it'll be fine. So then we have this relationship here. So I know that the concentration of H plus is equal to 1 times 10 to the negative 14th over the concentration of OH minus. So I can say concentration of H plus is equal to 1.00 times 10 to the negative 14th over the OH minus. So I have 1.00 times 10 to the negative 14th. That's a 1 and a 4. Divided by 3.16 times 10 to the negative 11. So again, I have to round here, but it'll be fine. So I can say that I have, and I'm going to put these in parentheses so that way I'm not going to get mixed up. So negative 14, close that parenthesis, divided by 3.16, negative 11, cool. So I end up with, let's see, 3.2, then 1, 2, 3, 4 times 10 to the negative 4 molarity. Now, because it's only had one digit afterwards, I probably should have only done this to one sig fig. I didn't. It's okay. I doubt their AP exam would actually even, they don't really care about the sig figs when it comes to pH and pOH because it's just kind of funky and there's a lot that you got to do with it. So for H, the concentration of hydroxide ions in calcium hydroxide, so we're figuring out, we have this, is 1.4 times 10 to the negative 4. We have to jump over and get to down here for the pH. So this time I will go this route. I'll go from OH minus to POH and then POH to pH. It doesn't matter why. You just do whatever one feels right to you, whichever one you feel that you might be better off with. Or you might remember the equations for it, because you do need to remember these equations. So POH is equal to negative log of the OH minus concentration. We have 1.4 times, oops, whoa, I jumped the gun there. Negative log is times 1.4 times 10 to the negative 4. So my negative log of 1.4 second EE to the negative 4 is equal to 3.85. And I also know that my pH is equal to 14 minus my pOH. So again, ideally I wouldn't round in here, but I could say maybe 14 minus the second answer gives me this. 14 minus, and then if you're doing this on an AP exam, you can say minus 3.85, or you can say see previous answer, or you can merge the two equations together, and that's kind of fun. Said no one ever. 10.1 would be your pH for this. So if we think about this, this ends up being a little bit more on the basic range, which makes sense because you've got a lot more hydroxide ions. If you're thinking, we have a lot of hydroxide ions in there. For I, the concentration of hydrogen ions in perchloric acid is 8.7 times 10 to the negative 3 molar. What is the pOH? So I have this. I want to get down here to the pOH. So pick either route that you would like to go through. Maybe I'll do this route. So I can say that my pH is equal to my negative log of my H plus concentration. So this is equal to the negative log of the, let's see, 8.7 times 10 to the negative 3. So negative log of 8.7 times 10 to the negative 3. That gave me about 2.06 for my pH. Now I know that pOH is equal to 14 minus my pOH. So I have 14 minus 2.06. So I can say 14 minus 2.06 gives me 11.94. And so that is my pOH. So this is also in the basic range because it's above 7. And my last little one here, the pH of an unknown solution is 13.2. So I know my pH is 13.2. What is the concentration of hydroxide ions? So I am here. I need to get to there. Let's go this path. And again, just because I feel like it. It has no rhyme or reason which one you choose. So my concentration of H plus is equal to 10 to the negative pH. So this is equal to 10 to the negative 13.2. So second log. And that was what? Negative 13 8.2. So this gave me 6.31 times 10 to the negative 14th. And then I can say that my OH minus concentration is equal to 1.00 times 10 to the negative 14th over my H plus concentration. So that is 1.00 times 10 to the negative 14th over 6.31 times 10 to the negative 14th. So actually, let's put these in parentheses. Negative 14, close out that, divide that, 6.31, and then that's negative, can't read my handwriting, I think that's negative 14. Sure, we're going to go with it. And then our pH here is equal to 0.16. Or sorry, our OH minus concentration is equal to this. And because it is concentration, molarity is our unit. And let's think, does this make sense? Well, the pH is really, really high, so you know that you're going to have a lot of OH minus ions. So yeah, you're going to have a lot of ions right over here. And this is all going to be below 1, so the thing anywhere closest to 1 would give you the most amount of ions. So hopefully we're able to go through all those. Remember, I would suggest remembering those potentially 4 equations, and then from there you can work through to get to the rest of them. Good luck on some practice questions. Take care. Bye.